All right, welcome everyone. We are back live with not one, but two engineers from the DevRev team. Just a quick reminder to folks who have been joining us over the last several weeks. If you missed any of these live streams, you can find them on YouTube. Just search for DevRev, and we've got weekly shows that you guys can watch. They're all 30 minutes long, and they all talk about deep technologies that are critical to what we're doing at DevRev, but also very interesting if you're interested in AI and analytics and workflows and any of these core technologies that are quite popular right now. Today, we have the pleasure of having Ritesh, who you've met before, but also Shanae. So welcome both of you.
Hi everyone, great to be here.
And where can we find you? I know Ritesh, you're in Austin. Shanae, where are you right now?
I'm in India in a city called Surat, which is in Gujarat, which is in a state called Gujarat of India.
I mean, it's popular. I think it's popular for like gem trade, right?
Yes, Surat is very popular for diamonds and textile.
And food, apparently food as well.
Yes.
Okay, so enough about Surat. Let's get to LLMs. I think the last time we met, we talked a little bit, and it was just myself and Ritesh, but we talked a little bit about the idea of when is it the right time to actually start to think about getting beyond prompts and looking into fine tuning and post training and things of that nature. So that's where we started the conversation, and where we want to go today is to really kind of focus on how do you decide what the real model is going to be, the base model that you're going to use to actually do post training, because that's a very important selection. And so we want to spend an entire half an hour just talking about that base model selection. So maybe we can start with the usual suspects and what makes them effective, how they've kind of gotten to where they are. Shanae, you want to get us going on that?
Yes. So let me also, yeah, just a second.
And I think while you're setting that up, Ritesh, like obviously we got pretty excited about Llama and Phi, a couple of years ago, and since then, I know personally we've been using a lot of Qwen 3 models, and then more recently, GPT OSS got announced. So a lot of interesting new players as well. So I'm quite keen to see how things are developing.
Yeah. We are on top of all open source models. Our current fine tuning pipelines are upgraded to use Qwen 3 models, and we are also exploring GPT OSS models.
Got it. So what are we looking at here? Is this Hugging Face?
Yeah. Handler, I'm not sure if my screen is shared.
Yeah, it's on.
Like it's all right. So yeah, this is Hugging Face. It's where everyone uploads their open source models. So we have two models side by side. One is Qwen 3 8B, which is a part of the Qwen 3 series. Qwen 3 series has several models ranging from zero 0.6B to as big as 235 billion parameters. And we have seen that Qwen 3 is very, very good for fine tuning, uh, especially supervised fine tuning on downstream tasks. Secondly, we also have on this side Llama 3.1 8B instruct, um, which is again a model in the Llama 3 series, which is an 8 billion parameter model. Uh, Llama series also has models of varying sizes, but Qwen 3 is generally preferred over Llama because it is, yeah, we have found that it's better to fine tune Qwen 3 and it's more adaptable. So yeah.
Okay. But what is it about Qwen 3 that makes it more adaptable, though? Like, what is there anything about the way it's been trained? I mean, obviously they're the same size, parameter-wise, they're the same size. What can you tell us, like what you've observed that makes one better than the other? And yeah, just say more about that.
Right. So the first thing is that Qwen 3 is a superior model as compared to Llama 3.18b when you look at the benchmarks. Secondly, Qwen 3 supports both thinking and non-thinking modes, so you can switch between them according to your ease. And thirdly, it's the it's the uh, I suspect that it's the data that Qwen 3 is trained on that is making it such adaptable. We don't have access to the open data, but yeah, I mean, they have actually tailored the model so that it's easier for post training
Got it.
for downstream tasks. Yes.
Understood. So, I mean, you mentioned benchmarks. Maybe Ritesh, perhaps we can look at the benchmarks as well.
Yeah, let's have a quick look at the benchmarks. Yeah,
And before we get too deep into the benchmarks, I mean, we talked about Llama and Qwen 3, and you kind of mentioned in passing GPT-OSS. But I mean, there's been other models that have served as good base models, student models, if you will. Tell me, like, what has this looked like? What's the journey look like over the last 2 or 2.5 years? Like, are these the ones, or have there been other players that have come and gone?
yeah. There are a lot of players that have come and gone. If I were to give a quick time lapse, it all started with Llama. When Llama model was released, it's one of the best models, best open source models out there, which was performing as good as GPT 3.5. And from the Llama series, there's other models from Mistral. Mistral also released some open source models which were also good for fine tuning. And then we had Phi, which are especially have Phi has really good performance on benchmarks compared to their size. So there were Phi 14B and Phi 28B, and uh, now we see that Quen 3 is the leader in this. So one trend that we notice is whenever a new open source model releases, it's usually trained on more data and it's usually more up to date in comparison to the older models, because much more effort is gone uh, into the new open source models. So it makes sense for everyone to just have a look at the benchmarks and then make a decision for themselves. Do they need to switch their
Okay.
model or
So
not?
let's look at those benchmarks. And I know, Shana, you had it pulled up for a second. Let's go back to those benchmarks then. What are we looking at? When we look at the benchmarks, what do we want to look at?
Uh, right. So I can talk about this. So currently I have pulled up the benchmarks for all the frontier models, and this is artificial analysis, which is a very popular site for these benchmarks of AI models. This is the artificial analysis intelligence index, which incorporates 8 important benchmarks, right? And you have all these frontier models with these performances. Just to set the standard of where we are right now with the best of the best models, we have GPT-5 with the highest level at a analysis intelligence score of 69, and then following. So we can build from here. Yeah, but Ahmed, if you have any questions or anything too.
Yeah, I mean, look,
Yeah.
this is sort of an amalgamation of different evaluations. MMLU Pro, Humanities Last Exam. Some of these names even sound pretty daunting. Maybe you can talk a little bit about what these are, and also like what artificial intelligence is actually offering. I mean, we understand Hugging Face and what it's doing, but how has artificial analysis sort of like served a purpose in sort of benchmarking and providing transparency around performance?
Right. So yeah, let me start by talking about the benchmarks. So these are public benchmarks which are prepared to evaluate quality of the large influx of LLMs that we are seeing. Just to like give a summary of MMLU Pro, it is a benchmark that covers different aspects of science, math, history, etc., and it tests the general intelligence and the general awareness of the model.
Mm-hmm.
Then you have live code bench, which of course checks the performance, the coding ability of the model. You have AIME, which tests the performance of the model on math. So yeah, these different benchmarks test different abilities of the model. And to answer your next question, artificial intelligence is uh, an open platform where everyone can right. So you have all these different models, you have all these different evaluations, but it would be very good if you could have one place where you could see the performance of different models on different evaluations. You could see the latency, you could see the throughput that these models give, and artificial analysis does that for you.
Got it. Okay. Let me ask you this: like, what practically speaking, when we're trying to make a selection, it's not like we're just gonna take the top, open weight model from this list, right? Like, what does our criteria look like when we want to make a decision on a model to start with when we need to do some post training?
Right. So, yeah, Ritesh, if you want to take this
Yeah,
question, or
maybe I can chime in here. It actually depends upon the task. So yeah, if you if your downstream or domain specific task is more logical and math like, you would probably worry about AIME benchmark, and you would just see a model or take a model that's scoring top on AIME. But if it is something that's agentic, then you can take humanities last exam or live code bench, which are both coding and test the agentic capabilities of models. If you want to build your own benchmark, or if you have agents and you want to build your own tasks, there's also terminal bench where you can build your own task that you want to use, and that way you can actually test these models on your own task, so that you have a better evaluation, because not all benchmarks might capture something that you want.
I get it. So I mean, now we're looking at terminal bench. There's also SWE bench. We've heard of many of these
Yeah.
evaluations. How do these make it into this artificial analysis index? Now, I imagine this artificial analysis index has evolved, as have the evaluations themselves. So it's not like we have an incredibly consistent index for the last several years, right? I mean, this is
Right.
heavily influenced by what's happening in recent months. Like, how do you see this further evolving? Are we seeing an index that's going to be a compilation of more evaluations? Are we going to see SWE bench or terminal bench show up in this index at some point in the next 2 years? Well, how do you see this moving forward?
Yeah. Yeah, if the way I think it will be is, there will be some index in which all benchmarks are combined and given. Currently, artificial analysis more or less is a comprehensive list of that benchmarks, and for every use case, for every person, they need to build their own sub projection of what among those tasks are actually relevant for us. And also, yeah, the reason why we keep talking about artificial analysis is they're doing a great job in actually identifying and running the evaluations independently. Even closed source model providers, when they are releasing the models, they are actually giving them uh, access to the model so they can test it, and along with their model release, they are also giving an artificial analysis as a single standard score. The our index might change, but the idea of having a comprehensive benchmark list and then having a subview of that for your use case remains the same.
Yeah, makes a lot of sense. Now, I mean, going back to that screen, we saw some of those tabs right up top. If Shanae, you take us back onto artificial analysis. You see reasoning versus non-reasoning. You also see open weights versus proprietary. Tell me about open weights, like what that means, and then maybe we can also talk about the emergence of sort of open weight mixture of expert models specifically. But let's start with open weights. Like, obviously, when you're going to do post training, you need an open weight model. Am I right?
yes.
So say more about that. Like, what's the difference between having a model that's open weight versus an open data model? Like in our particular case, an open data model might be important from an academic perspective, but as it pertains to fine tuning, it really serves us no advantage, right?
Yes, I mean, open data provides some more visibility into what the model is trained on. But I don't think that's very essential when you go to the downstream fine-tuning tasks. It adds some value, but not a very large value. Whereas if you compare open weights versus proprietary, you definitely need open weights
Right.
to fine-tune. Yes.
And let's just click on that open weights versus proprietary, because really, if you're going to do fine tuning, what you're betting is that by using an open weight model and tuning it for your task, you can get excellent results, even though perhaps there's a proprietary model that on just generic benchmarks can perform better. That's the promise. I mean, unless you're looking for something other than accuracy or performance, you're looking for maybe other gains. But particularly here in this particular, if you were to zoom in a little bit, it seems to me that at the very top you have um, basically all the proprietary models. What's the number one open weights model in this list?
Oh,
It's
it's the Qwen 3
Qwen 3.
235B.
Okay, Qwen 3.
Yes.
Okay, and
Yeah.
64 and 69. I mean, like, is that going to be something that's perceptible for the types of tasks that a business might have? I mean, like obviously it's an amalgamation of many different benchmarks, but like how do you qualify that? Like 64, 69, like what does that mean to a human empirically speaking?
Right. Empirically speaking, 69 and 64 both are really, really good scores based on the current level of intelligence that we have achieved using LLMs. And again, these are very, very big models. 235B, GPT-5. We don't know how much, but it should be very, very big model. So again, these are really high numbers. If we just want to speak empirically, 64 is not bad at all.
I mean, let's put it this way: in a business setting, if you're asking questions about your data or you're taking actions against your work items and so on, I mean, are you going to be able to tell the difference from this perspective? I mean, forget fine tuning, just on the basis of the Qwen 3 model here, the first blue one, and then if you look at the top of the line model, I mean, are these things that we can actually perceive a difference, like at the human level, or how do you characterize that?
Yeah, maybe
I think you can
jump
perceive a
in here.
difference. Yes.
Yeah, there will be a little bit difference that can be perceived. However, also the 64 and 69 is an amalgamation on all the benchmarks.
Exactly.
For your use case, the difference between 64 and 69 might be even close. So from our test, what we have found out is for simple tasks like writing and rephrasing and then just summarizing or given context, operating on top of context, we don't really see much of a difference. However, if the task complexity becomes much more high, long agentic, for example, then you start to see some differences between these things. So there, even though we have the difference, our idea is there probably it's not 64 65 or 64 69, it's probably 34 and 39, because that's a harder task where both of these models struggle. So our hypothesis, we can take this 34 to maybe 50 or 70 with post training.
Got it. And again, on the topic of mixture of expert models, can you say something about that as well, Ritesh?
Yeah, so we have seen that more or less everyone's moving towards mixture of experts architecture. If we can bring up the architecture difference, yes. So this, what we are seeing on the screen is on the left side we have GPT OSs, on the right side we have GPT-2XL. I mean, just a recap, like we have transformer block, and the difference between mixture of experts versus this model is here in this GPT-2XL model, all the weights are activated at once, whereas in mixture of experts, there is a router layer, and you define or you kind of sparsely identify and activate your model. So that's the difference. The idea is maybe uh, with this with having multiple experts and having this sparsity, you can train better and also represent your data better.
Got it. I mean, is this sort of the is it, and you're seeing this like all the top open weights models right now are mixture of experts models?
Yes, and I must say, mixture of experts models also provide you a benefit during inference, because uh, because not a lot of parameters are activated at once. What you see is potentially your inference time goes down, latency goes down. However, your GPU costs are gonna remain the same, because you will be loading the entire model into memory. For example, we have here Qwen 330B on top, so you're gonna consume 64 GB of GPU, but while during inference, it's, I think this has 3 billion activated parameters, so it should be a really fast model.
Got it. So you're saying time to first token is going to be better?
Way lower. Yes.
Okay, significantly. Okay, fantastic. Where do we want to go from here? Obviously, size, distillation, topics like that. I mean, when you're selecting a base model, how much does this matter? If you're training a 7 billion parameter model versus a 14 billion parameter model, how do you want to think about that? Should people have a framework in mind in terms of making that selection?
Yes, I think if I were to explain framework or algorithm, what you would do is you would start with the benchmarks, which we have already covered. Let's say you found your candidate set of models.
Yep.
The recommendation that we give is first start with a relatively larger model. I mean, don't try to fine tune Qwen 3.6b, even though if it's doing good, or very small model doing good on benchmarks. Usually, from our experience, what we have found out is smaller models are harder to train or harder to distill. So it would be better if one can start with 8b or more. Ideally, the bigger the better, but 8b models are 8b or 7b models are a good place to start with. And as and run all your experimentation suite there. The reason why we like 8b is it fits into one single H100, and your training can be done better. You don't need to split the model across multiple GPUs. Once you iterate on top of 8b, depending upon your latency requirements, then you can see if you need to further distill this into a smaller model.
Got it. Like understanding how well a base model does with distillation. Now, like how is that measured? Because I know that not every model distills as well as the other. So there are some real differences there. And if, let's say, that is sort of an intention that you have after post training, how do you evaluate like sort of the viability of different models in that regard?
Yeah, maybe we can actually reflect a little bit on why are we seeing this difference. That is, we see a lot of models which are doing good in benchmarks, but only some models that are being distilled well.
Right.
My hypothesis or suspicion is that perhaps some of the models do good on benchmarks, but their pre-training data doesn't cover entire domain distribution or entire internet. And the models which we see are distilling better are the models basically which are trained on have diversity in their pre-training and also in post-training. So now, how do you know? Because people are not releasing their data distribution. How would you know which model, or how do we know that Qwen 3 distills well? This is mainly based on experimentation done in the community. That is, people try fine-tuning every new model and then report results. So, and even we have done fine-tuned Qwen 3, 5, all 5 series and Llama. What we found out is actually Qwen 3 and Llama work for our use cases.
But even some of these academic models with open data, couldn't we use these to sort of support that hypothesis to say, listen, if you start to bring more diversity in pre-training and post-training, then you're going to find better distillation performance? I mean, like there's a way to validate this, right?
Yes. So when we talk about open data models, it's either open data for post-training or open data from pre-training. There's only one or two models which are built on top of open data for pre-training as well. They are by Alan AI. However, it's the Olmo and Tulu series of models. However, they don't perform as good in the benchmarks. And recently, we are seeing a trend of open weight models during post-training. There, even though the post-training data is open weight, it's usually fine tuned per a particular task, or for just inducing reasoning on a non-reasoning model, which might not be much relevant to your domain specific task.
Okay. And since you brought up reasoning and non-reasoning, so Shani, coming back to you, like how do you build in reasoning? So meaning to say, if you want to have a really good post-trained, fine-tuned reasoning model, what's the way that you think about it? Do you start with a reasoning model and you make it better at reasoning? Do you start with a non-reasoning model and try to make it good for your specific domain as it pertains to reasoning? How do we think about that? What are the pros and cons?
Right. So I would like, based on my experience, like if you want to have a final fine-tuned reasoning model, you should definitely start with a model that already has reasoning capabilities. Now, even there, we have two types of models. There are models which are only reasoning models, such as your GPT OSS models, and then there are models which are hybrid, which is that they support both reasoning and non-reasoning modes. Now you can go with either one of them, but starting with a non-reasoning model and then making it a reasoning one uh, should not be the ideal way, because you are going against the post-training history of the model, where it is trained to not reason, and then you are with, and then the post-training data that they have done, that the model already receives, is much bigger than what you generally do during SFT. So you should ideally not go against it, and start with a reasoning-based model.
Got it. And well, by the way, we're probably gonna have a few more minutes of discussion here, but just a general reminder: people who want to continue this conversation, we'll have subsequent parts in this series. So you can look forward to that. But most importantly, you can join us on our Discord community. Our Discord server link is being shared here. So you guys can feel free to join us there. And folks like myself and Shanae and Ritesh will respond to your questions and maybe join you in a real dialogue there as well. But coming back to reasoning and non-reasoning, is there anything else, Ritesh, that you'd want to add on that topic? Is there any reason why you would want to start with a non-reasoning model if you're looking for fine-tuning like a thinking task?
Yeah. Again, the difference between reasoning and non-reasoning is actually reasoning gives you an adaptive computation. That is, you generate more tokens before giving an answer. So essentially, you're not learning just a function. You're learning a function that has test time compute, or compute is different. Now, to the question of, okay, now I've decided to fine tune, should my data set be have reasoning or not? It depends upon the type of task you are fine tuning. Especially, for example, let's say if you know, okay, my data set covers my more or less covers my entire distribution, and it's all I need is, here I need to, for this input I need to learn this output, or for this input behave it like that. In this case, you don't really need adaptive compute, because your data set has a well cover of the distribution. In which case you probably don't need to do non-reasoning fine tuning. However, let's say if your data, what you're training for is winning IMO gold medal, or somewhere where you are actually when you're testing it, the model will see some examples where uh, such examples were not seen in training. Then that's when you would go for a reasoning dataset.
Got it. Okay, fair enough. I think it would be good for in a subsequent series to actually show some examples of us fine tuning either and what the
Yeah.
intended purposes were. I think that would be really, really good. We've got a couple of minutes here. Where do we want to go? Do we want to talk about LoRa fine tuning and how that influences model selection, or are there other topics, Ritesh?
Yeah, Shanay, can you let's talk a little bit about LoRa. Can you explain the difference between LoRa and normal fine tuning, and also bring up our experimentations?
Yes. So, yeah, just to bring up the experimentation, could my just screen be put down for a minute?
This is getting serious. No, I'm kidding.
Yeah. Um, yeah. So, like, is my screen? I'm not able to tell if my screen is. Yeah.
It's coming
Yeah,
back.
it's coming up.
Yeah.
Okay. Okay.
Actually, we see the same paper.
Yeah, it's the same
Yeah.
preprint PDF. Did you want to show something different?
Yeah. I wanted to show something different. All right.
Okay.
I will. Probably I can quickly go here and just start here. Yeah. So this is one. First of all, to explain the difference between LoRa and full fine tuning. In full fine tuning, you basically train all the weights of the model. Uh, so, for example, if you are going to fine tune an 8 billion model, you will be training and updating all the 8 billion weights if you are going for a full fine tuning. But if you are going for a LoRa fine tuning, LoRa only trains, say, 1% or 2% of the parameters that your model has, and it is a very well established method, and it can get you the same results. It uses low rank matrices to update the weights, and to point out its advantages, uh, I have here an experiment where I load an entire model. This is a Qwen 332B model, and as you can see that the loading time that it has.
Vinay, could you zoom
uh,
in a little bit?
yes,
Increase
yes,
the font size. Yeah,
yes.
this is good.
So
Thanks.
yeah, as you can see over here, the loading time that it has is 156 seconds, which is around 2 minutes and 30 seconds. So now say you have multiple use cases in your production environment, and you train a different model for each of them. Then how do you switch between use cases? You would have to load a model and then unload it when you want to uh, go for another use case, and every
Right.
time you unload a model and load another one, you get this a latency of 2 minutes 30 seconds just to load that model, which is very high. But when it comes to LoRa, you can quickly unload and load the LoRa adapters in 15 to 20 seconds. And that is a very, very big difference. So when you are serving multiple use cases, you can have multiple LoRa adapters. This is just me talking about the latency, but you also have benefits on memory. Because your LoRa adapter is much only 1%. So yeah, memory is also very, very less.
Yeah, and of course, modern model inferencing infrastructure providers, they're gonna have way better load times, obviously, but it's all relative.
Yeah.
Yes.
And obviously, nothing's for free, right? But coming back to LoRa, if it's so efficient and the load times and the size on disk and everything is better, it can't be a silver bullet. Like, what are the trade-offs? Like, what are the disadvantages to basically doing LoRa fine tuning versus traditional fine tuning of a model?
Yeah, maybe I can chime in here. Like that's a really good question. Like if LoRa works, why don't we even pre-train the models with LoRa, right? Why
Yeah.
do we even allow all weights to be updated? That's because the at least the LoRa paper and from our experimentation as well. So initial pre-training and getting the model to an base model or base FFT models stage, the difference between your random initialization and that the final model, that's not low rank. Basically there the weight or the power of expression needs to be very high. That is, you need all weights to be updated or all weights to change.
Yep.
But the idea is now from this point you have a good base model to a fine-tuned model. Now this delta can be of low rank, and even in lower rank matters. That is, if you keep your rank to be 8, that is, you decompose your matrix with a rank 8, it allows you to move a little bit. If you keep on increasing the rank, or if you max it out, then you will reach the full fine tuning or changing all the parameters. The what you are changing is essentially how much can I allow my model to change. So more or less, the idea is models are already at a place where the differences or the uh, changes that we need to do for more tasks are actually can be expressed using low rank. However, there can be some tasks which are very complicated and cannot be done with low ranks, and you actually need high ranks or full fine tuning.
I mean, just practically speaking, how do you make that determination? Or is that maybe something we can save for a different day? Because I am interested to know, how do we decide if you can do with just the low rank matrix versus, having to do something, maybe not having that be an option. I think
Yeah.
it's an interesting topic. Like, when is a LoRa adapter not enough for fine tuning? And also, a quick question related to that: how do you, if you decide that you're going to be doing LoRa based fine tuning, how does that have implications on which base model do you select, or is it the same no matter what?
Yeah, on the first question, it's actually like everyone faces the question, what's the LoRa rank or what's the alpha to select and everything. So there are some set of defined configs. Essentially, everyone starts with rank 8 or more. However, for our use cases from our experimentation, we usually do a rank sweep at any point at one point of time, do an eval and see how much is the difference between LoRa low ranks, I mean 8, 64, 512, and full fine tuning. If we don't observe a difference, that's when we actually go to a LoRa rank. So it's like we kind of do a binary search on the rank, and we
Got it.
arrive at the rank. And from our analysis or experience, we see that LoRa with the 64 rank more or less works even for our complex tasks.
Got it. And in terms of how, if you have an intention to go with sort of LoRa based fine tuning, does that influence which base model we go with, or are those things orthogonal?
They are orthogonal, so
Okay.
it shouldn't influence. All models are transformer blocks, so you can decompose and add adapters on top of any model. One thing though is when you are doing LoRa, the amount of memory that you require for fine tuning is also less. I mean, uh, base model. Let's say you're fine tuning a 30 billion model, you will load 30 billion, or depending upon your quantization, you'll perhaps load around 60 GB VRAM of GPU, and how many parameters you're updating, you need that much more extra memory because you need to store their gradients as well. Because LoRa updates less parameters, you can potentially have less do do good with less GPU memory. But for full fine tuning, it's usually into 3x because gradient updates are usually in FP32 in comparison to the base model being in float 16 or B float 16.
Got it. Makes a lot of sense. All right, so we've gone a little longer than usual today, but I think we covered a lot of ground. Shanay, Ritesh, thank you so much. I guess, folks, you can find us on Discord, you can find us on YouTube, and you'll find us here again next week, but we'll discuss another topic, and I'm sure we're going to have Shanay and Ritesh back here to get into maybe part 3 of this series, and I look forward to that as well. Thank you, both of you, and thanks to everybody who joined us. Take care. Bye.
Thank you.
See ya.
Bye.